Okay, so we are going to go over worksheet 3b, where we're going to look at some examples of quantitatively working with conservation of energy. And so the first part of this problem deals with a moving cart that hits a spring. It's traveling at 5 meters per second at the time of contact with the spring, and at the instant that the cart is motionless, we want to know how much the spring is compressed. So if we describe the system, if you want to include the ground or not, that is optional, but I would also include the spring in the system. So we know that the cart is carrying with it kinetic energy. When it hits the spring, it will do positive work on the spring. The spring will do negative work. That means the spring will rob the cart of its kinetic energy and store it as elastic potential. So the energy that was once in the cart is now going to be in the spring. So if we include the spring in our system, then we can include it in our diagram. So here's our LOL energy flow diagram. We have to include this O here for our, which will be our system, our storyboard. And so just to qualitatively begin our diagrams first, we'll just indicate that at the very beginning we have all kinetic energy, that the kinetic energy is transferred into elastic through the work that was done by the negative work done by the spring, and all that energy is now stored as elastic potential energy. So that allows us to make an equation that relates what happens before and after this interaction. So what we can say is that EK at the beginning equals EEL at the end. And anytime I have energies on the right, which are final energies, I'm going to just put a little prime at the top, this little apostrophe, just so that there could have been, let's say, in some examples, some kinetic energy left over. And I don't want to get my kinetic energy that I had before mixed up with the kinetic energy that I have left over after. So the way I'm going to denote those differences is with a prime. So our goal is to find how much the spring is going to compress. Now, that's going to be in the elastic potential energy term. But first, I do ask for quantitative values on your bar graph. So if we can at least calculate the kinetic energy, then we'll know what the elastic potential energy is. So EK equals 1/2 mv squared. 1/2 times 8 times 5 squared is 100 joules. So there's 100 joules before. There better be 100 joules after. It's just in a different form. There is 0 joules of EK. We had 100 joules of EK, but now after this collision, we have 0 joules of EK, but 100 joules of EEL. So now we're going to find the compression of the spring, which is delta X. So we can bring out our EEL equation, which is 1/2 K delta X squared. Since EK equals EEL, and we established that on our bar graph as well, the amount of EEL I have is 100 joules. K is 50, so I'm looking for delta X. So I solve this for delta X. I multiply both sides by 2, divide both sides by K, square root everything, so I get 2 EEL over K. and we get a value of 2.0 meters. The next problem, number 2. We want to determine the final velocity of the cart assuming that 10% of the energy is dissipated by friction. Alright, so here we are definitely going to worry about friction. So what type of energy do we have to start with? It's not moving, so there's no EK. It is 5 meters higher than it will be later, so we have to consider EG. There is no springs to worry about, so there's no elastic potential energy. So we're saying that at this point there's all EG. Now, as the cart goes down the hill and there's friction, we're gaining speed, but not as much as we could, because some of that energy is also going to EQ. And that's the work that is being done, the negative work done by friction. So we're told that 10% of it's dissipated by friction. So 10% of the 100% that we had initially is EQ. The rest of it is EK. So it will be just shy of reaching the top line there, and EQ is small. So this is 90%, 10%. If we want to quantify that, we'll figure out how much EG there was to begin with. That's MGH. So we have a 20 kilogram mass. We multiply that by 10 newtons per kilogram. And the height is 5 meters above the ground. So you get 1,000 joules. So this is 1,000. 90% of 1,000 is 900 joules. 10% of 1,000 is 100 joules. So we're asking now how much, what's the new speed? Well, since we only have 900 joules left of kinetic energy, we're going to use that value to work out the velocity. So we're going to solve this expression now for speed, v, which is the square root of 2ek over m, and ek is going to be 900 joules. So you'll get a value of 9.5 meters per second. What if there was no friction? What kind of speed would this cart have at the bottom of this hill? Well, with no friction at all, we'd have 1,000 joules of kinetic energy. So if you plug that in to this formula, plug in EK equal to 1,000, you'd get 10 meters per second. So that is the fastest it could ever go, given that it's only being accelerated by gravity. But it could be any value less than 10, depending on how much friction there is on the surface, and that'll determine how much energy it loses along the way. Okay, let's move on to the next problem. Number 3. Block is placed on a spring that's compressed 0.3 meters. What height does the block reach when it's launched by the spring? I'll do a little LOL chart. So again, in no particular order, we're going to ignore air resistance here. So I'm going to have EK, EG, EEL, EK, EG, EEL, and I'll put EQ just so that we remember to do that in most cases. although I'm not going to worry about air resistance here, so we don't have to worry about EQ. The only energy it has is elastic potential, because it's not at any new height yet. It will go higher up, but that's later. It's not moving yet, but it has compressed the spring, so all that energy is inside the block spring system. When the block starts to go up, that is due to the fact that the spring is transferring energy into the block and making it move, so there's kinetic, but it's also making it rise up. So eventually all of that elastic potential energy will be gravitational potential energy. And that's the case that we have here. The final velocity is 0, so that means the final energy is just all Eg. So we can set up the formula that EEL equals Eg. And I'm going to bypass the stage where we find what the actual values of the energy are and look for the final answer by doing some algebraic substitutions. So we know that EEL is 1/2 k delta x squared. And we know that Eg equals mgh. So from setting up our formula that describes the conservation of energy, then we can now solve for h by dividing both sides by mg. So h equals k delta x squared divided by 2mg. And this 2 here is that half. So k is 100 newtons, newton per meter. Delta x is 0.3 meters. The mass is in grams. You got to get that into kilograms, so that's a 1/2 kilogram. It's important for all the units to work out. So you get a value of 0.9 meters. So the block will rise up to a height of 0.9 meters higher than where it starts. Okay, let's go on to number 4. Alright, so the bullet strikes a block of wood which exerts on average a force of 50,000 newtons opposing the motion of the bullet. How far does the bullet penetrate the block? Okay, so clearly this bullet has kinetic energy. It's moving at 350 meters per second. Really, really fast. So we're going to give this bullet a lot of kinetic energy. Now, when it hits the block doesn't store the energy. It's not like hitting like a trampoline where the bullet can bounce back the other way. The bullet lodges itself inside of the block and then comes to rest. So that means all of the energy is out of the bullet and in the block, and so that is all EQ. So we can certainly calculate all of the kinetic energy because we have the mass of the bullet, which if it's in grams you got to get it into kilograms, so that's 0.025 kilograms, and all of that is going to be transferred as EQ. Well, EQ is the energy that is robbed from the bullet from negative work that was done by a force inside the block, and you're given that force. So we can say that EQ equals the work done by that force, which is F times delta x. So on average, this is the average force On average, the block exerts 50,000 newtons of force opposite to the motion, and delta x represents how far into the block the bullet can go. So if we can calculate the kinetic energy that this bullet has, we'll know how much energy it loses to the block, and then with the block exerting that force, we can figure out how far the bullet is able to go into the system. So again, let's just approach this without getting the total energy. To save some time, we have 1/2 mv squared, and that equals F delta x. And I'm looking for delta x. Let me use this space here. So delta x equals mv squared over 2f. So 0.025 kilograms times 350 meters per second, the whole thing squared, divided by 2 times 50,000, and you get 0.031 meters. So it lodges itself 3 centimeters into the block. So it was moving very fast, but 50,000 newtons is a huge amount of force. So that's why it wasn't able to move that far. All right, the final problem comes in a few steps here. So we have a 200 kilogram box, and it's being pulled at constant speed by a little engine, and it's moving over a distance of 2.5 meters, and there is friction on this surface, which makes sense because it's moving at constant speed. So first we're going to draw a free body diagram. We're going to quantify it. So we have FG. If it's a 200 kilogram box, it's 2,000 newtons. FN, 2,000 newtons. And we have a force that's pulling it to the right. I'll call that tension. And we have a force of friction to the left. And because it's constant velocity, these two forces balance. Friction equals mu Fn. So 0.2 times 2,000 is 400 newtons. So if this engine is pulling this box at constant speed, then it must also be exerting 400 newtons of force. If we were to draw a diagram for this situation, we label all of our energies. Before and after we have to also include EQ. We know that it's moving at a certain speed, so we'll give it, this is kinetic energy here. It's not changing height, we don't have to worry about EG. There's no springs attached, so there's no EEL, so that's pretty straightforward. We start with all EK. Now the speed doesn't change. So what about this, all this, the fact that this force from the outside, you know, the engine is working, it's consuming fuel, that because the engine's outside of our system, then we don't have to worry about it. But this is an external force, and it's doing work on our system, but it's not causing it to speed up. So there's no new kinetic energy. So whatever kinetic energy you had to begin with, you have the same amount. These two should be equal. Same amount. Right? But there is work being done by the engine. But all that work is going into EQ. So we are increasing the amount of energy in our system, so we have more energy than we did before. But because this EK equals this EK, the only real change in the energy is whatever work was done by the engine will give us the amount of energy that's loss to friction. So if we want to find the amount of energy transferred in by the engine, we could just take the force of tension, multiply it by the distance that it covers. So tension is 400 newtons, the distance is 2.5 meters, so the amount of energy must be 1,000 joules. So that's 1,000 joules lost to EQ, because if there was no friction, that 1,000 joules would have went to making EK larger, and that would have caused the box to speed up. And that's precisely what Part D is asking for, the fact that if the engine pulled the box with 500 newtons of force, which is greater than 400, the friction wouldn't change. So that means there would be an unbalanced force. The system would accelerate because the net work being done on the system is positive. There is more work done by the engine than negative work being done by friction. And so EK will continue to grow, and so the box will accelerate. In number 6, it asks how far could the box in problem 5 be pulled at constant speed with an expenditure of 8,000 joules of energy. So we take the same formula here, and we assume that EQ is 8,000 joules, and if we divide it by 400 newtons, which is the tension, we'll get that for number 6, delta X equals 20 meters. So if this box is able to move 20 meters across the floor, that means that the engine would have used up 8,000 joules worth of energy. Alright, and that is a wrap for worksheet 3b.